Thank you very much for the nice introduction. Yes, I'll be talking about hierarchical modeling for digital twins, and this is a joint work with Professor Merman and Philip Schulz. And there are also colleagues that work on similar concepts. For the MRO project, there is Eshwar Ramasity and Hannes Danschel that was just mentioned for the HTA project. And I'm mainly working for the EA project. So what we are working on is on developing simulations for digital twins. But which mathematical models should we use in those simulations? We have mathematical models in different shapes and different sizes, from complex and accurate models to simple and fast models. So which ones should we use? And to answer that, we need to know what are the requirements by the digital twin. So the first one of the functions is feedback to design, meaning we use the data that we get from the machine to get better designs in the future, and for that we need very accurate models. The second one is condition monitoring, and for that we need real-time simulations because we want to react very fast to problems that may happen in operation. The third one is predictive maintenance, and for that we need models that are able to adapt over time to the changes within the machine. And finally, we need to basically store these models and the data. This is important for human-machine interaction and for the human to have a say in what's happening, basically. And from that, we get this hierarchy of models. So we start with the most accurate model, which is the partial differential equation in most cases. It's very complicated to solve, so it requires a lot of time, but it's the most accurate that we have. We can get results by doing a discretization. This can be more accurate using a fine grid discretization, but slower, and we can do coarse grid discretization, and we can get faster simulation. At the bottom, we have model reduction, where we can reduce the order of the system even more to get even faster simulations. And this can be tweaked or controlled by some tolerance if we want more faster simulations or we want more accuracy. Then on the side of that, we have lumped parameter models. So these are models that have a specific structure, generally specific to the application, where we need to identify just few parameters to know the model. And we can identify those parameters using measurements or from our discretized model. And these are usually faster but less accurate than, for example, the discretized model. And on the right of our hierarchy, we have general data-driven modeling using machine learning or other methods. So we apply our framework to electrical machines. So when modeling electrical machines, we have to take into account mechanical, thermal, and electromagnetic phenomena and their interaction. And for that, we have to use multiphysics modeling or coupling. And for that, we use the Port-Hamiltonian framework. I'm not going to details on that. If you want more details, you can look at our preprint here in the bottom. And basically, the system as an electrical machine has inputs that we call U, and outputs that we call Y. Inputs, for example, voltages, and outputs, for example, the torque. And then we apply our framework to each subsystem and also to the overall system. I will not go through all the models, but I'll just give you a brief example for the electromagnetic simulations. So we start from Maxwell equations for the PDE. We do discretization, and then we can solve, for example, for the magnetic field. Here is an example in ANSYS Maxwell for the magnetic field in 2D for an induction machine. And then if we are interested in particular inputs and outputs, U and Y, we can have a simple model as in the bottom, and then we can do model reduction on that and get faster model. For the electrical machine, specifically for induction machines, for example, we can get an equivalent circuit that is a lumped parameter model, where we need to identify only the resistors and the reactances called R and X here. So if we identify those, we basically have a model which is very simple. We can solve it very fast for the currents, I1 and I2, which represent the currents in the stator and the rotor. So this is very fast, but it may not be very accurate compared to a discretized model. And then on the right side, the general system identification is something we are still working on. There are other applications to this framework in gas and power networks, in discrete heating networks, in bioinformatics and other fields. There's also an application for this for additive manufacturing. I know a lot of people are working on this. But the paper that I'm citing here focuses more on the software stack and not that much on the modeling stack, although it mentions it. So if someone of you is interested in applying our framework to additive manufacturing or other applications, please feel free to contact me. And with that, I would like to thank you for your attention. If you have any questions, please contact us.